Hello, I'm David Silver from Udacity, and this is the fifth lesson of the Udacity Self-Driving Car Engineer Nanodegree program. It's called MiniFlow. This is the MiniFlow lesson in the classroom. The overview says, in this assignment, you will build your own neural network library from scratch. Your library, MiniFlow, will behave much like TensorFlow, Google's deep learning library. So let's take a look. We start off this lesson with a quick introduction from myself and my colleague Ryan Keenan, and then we dive into the mechanics of actually implementing a deep learning library. We talk a little bit about graphs, which is the mathematical structure that underpins how neural networks work. In a graph, these dots are called nodes, and these lines are called edges. And essentially, we can think of the nodes as artificial neurons in our deep neural network, and the edges are connections between the neurons. And you can see that neurons in one layer are usually connected to all the neurons in a previous layer. And these columns of neurons are each called layers. Over the course of the lesson, students implement this library called MiniFlow. So it's a little bit different than actually just implementing a single neural network. You're actually implementing a library that you can use to build as many neural networks as you want. And that's similar to what you get through Google's TensorFlow library, or one of the many other deep learning libraries that are out in the world. You start with forward propagation, and so you learn a little bit about how to propagate information and calculations through a network of nodes and edges. You actually implement forward propagation in code, and there's a quiz where you do that. You learn a little bit about layers and learning and loss, and how we go from thinking just about individual artificial neurons and connections to how we actually use layers of neurons to accelerate the training of the neural network. Sometimes this is called vectorization. Essentially, what happens is we can use the properties of matrices and vectors and linear algebra optimizations to make the calculations of a neural network really, really fast. Because instead of having to calculate each artificial neuron at a single time as we go through the network, we can run the calculations in terms of matrices and vectors. And that accelerates the learning and training of the deep neural network. Once we have kind of that architecture of the network set up, students learn about cost functions. This is a fairly common and important cost function called the sigmoid function. So if you think about each of those artificial neurons in a layer, they could either be on or off, or we could use a cost function like the sigmoid function, which is a little more nuanced than simply having a neuron be turned on or turned off. The value of the neuron could be somewhere on this function between 0 and 1. Once we run all the calculations through the network, what we want to do is figure out how accurate the network was. So if we put some inputs into the network and we expect to get the number 5 out at the end, and instead we see the number 3, what we need to do is figure out in which direction do we need to adjust the weights that are associated with each of those artificial neurons in order to get closer to the output, in this hypothetical case, call it 5, that we are looking for the network to produce. And we use a technique called gradient descent to essentially move downhill in a cost function and try and find the collection of weights that gives us the lowest error in our network. And so we use something called gradient descent to do that, and we propagate these changes in weights back through the network, starting from the output at the end of the network. So if we look at this output layer, we look at how wrong we are here at the end, and we propagate the errors back through the network using back propagation, adjusting the weights as we go, in order to train the network to produce the output that we'd like it to produce. And by the end of the lesson, students have their own miniature deep learning library. You're welcome to use it if you want, although the next step is to use Google's TensorFlow library, which is a really much more robust solution to actually build real deep neural networks that will do some pretty exciting things. But just learning how to build MiniFlow yourself will give you a great sense of how TensorFlow works, why it works the way it does, and how deep learning works, and some of the really important properties of deep learning, like using layers and vectorization and cost functions and gradient descent and backpropagation. It's a great introduction to that. So that's MiniFlow.